Hello, my name is Alexei Surin. Back in year 1993, Professor Kunii organized the International Workshop on Synthetic Worlds. At this workshop, very interesting ideas were proposed and discussed. How to build shared information spaces, shared virtual worlds in cyberspace. These ideas were later published in the book Cyber Worlds in year 1998. It followed by the first international symposium on cyber worlds in year 2002. Later in 2003, we met with Professor Kunii in Singapore, and after a long discussion, decided to start annual conferences on cyber worlds. He suggested me to take a leading role. He actually educated me how to organize conferences. I didn't do it before. And first we organized one conference in Singapore, one in Japan, then one again in Singapore. But after that, we decided that it's time for the conference to start traveling the world. And Professor Kunii was following the conference. At each conference, he was given a talk. Some of the conference he even co-chaired as an honorary chair. He was introducing to conference new people. He was always followed by young researchers for whom he was a living legend. Unfortunately, year 2016 was the last year that he personally came to the conference. Then he said he cannot travel anymore because of his health, and the conference continued without him. And we always remember him. This conference is his legacy. Thank you, Professor Kunii. We remember you.
I'm Wenting Dai. Let me introduce our paper, Detection and Segmentation of Image Anomalies based on Unsupervised Defect Reparation. Anomaly detection is the process of identifying outliers. They usually train what is normal in the training set, and during testing, what is different with normal will be predicted as outliers. It has been applied in various fields, such as cybersecurity, optical inspection in manufacturing, and medical applications. However, it's still a challenging task, especially when it comes to unsupervised pixel-level segmentation of anomalies in images. The recent works of anomaly detection can be grouped into classification-based and reconstruction-based approaches. Classification-based approaches, which are also known as one-class classification, aim at finding the best decision boundary, such as hyperplanes or hypersphere, around the normal class distribution and tells outliers apart. However, the modeling of distribution of highly complex and unstructured image is still difficult to apply for classification-based approaches. The recent success of autoencoders and generative adversarial networks has influenced the way of image reconstruction. Lots of reconstruction-based approach was proposed, but they are not free for drawbacks. This figure shows the result of two reconstruction-based approaches. The first column are the defective image and its ground truth. The rest are the reconstruct output and their detection result. For the cracked hazelnut, even the model only trained on normal images. The residues of defect information still cannot be fully avoided in the reconstruct output. In another example, the reconstruction-based method generates defect-free image at some level, but the images are quite fake. In their detections, the huge loss between the input image and the reconstruct output overwhelms the defect. Therefore, the detection results are still worse. We then hypothesize if the defect can be repaired in the reconstructed images, will the non-defect regions still look similar to the arranging? The defects will be clearly detected in the final residual maps. Therefore, we propose to detect and segment the image anomalies based on an unsupervised defect reparation process in which the impinging network will be adopted, which is used to complete the missing region based on the rest of the image. There are two stages in our defect reparation-based approach. The first stage is coarse reconstruction. It assumes the impinging network has learned to fill the normal content in the missing region after training on normal images. It first divides the image into several regular patches. The reconstruction of each patch can be done by filling the remaining parts of image into the impinging network. A defect that appears in one patch can be largely eliminated in its impinging result because the filled patch is not affected by its original defective pixels at all. If we impinge all patches with normal content one by one, a coarse defect-free image can be formed by combining all filled patches. Afterwards, we can get a residual map based on the input and the reconstruction output. In addition to the pixel difference, we also compared the extract feature map of convolutional neural network. It has been proved that the layers in the portrayed CNN network can extract meaningful visual features such as age, corner, even color distribution. Afterwards, we will get a binary mask based on thresholding method. During training, the binary mask will be get by also segmentation. In testing, we defined a new threshold based on the result we get. The second stage is self-supervised defect reparation. The suspicious region found in previous stage will be reconstructed in this stage again, since the region waiting for repair are more precise than previous. The reconstruction error in the non-defect region can be largely depressed. Therefore, the defect can be more distinguishable in the residual map. For differentiating the defective image, we define the sum of final residual map as the anomaly score for images. The final decision will be made based on the ROC curve. And for localize the precise location of the defect, we define a threshold as this formula, which assumes the pixel could be abnormal when their residual value are larger than the averaging upper bound of normal reconstruction loss, and the mean residual value of the test sample is used as an image-specific adapter. In order to improve the reconstruction accuracy, our approach makes two iterations of self-supervised defect reparation. We evaluate the performance on the recent published anomaly detection dataset. It provides 15 different categories of images. Specifically, there are 5 categories of textures and 10 categories of objects. We compared our method with 7 state-of-the-art benchmarks. We also extend our method into 4 different variations. The first 2 only use one type of difference in the residual map, and the others use the combined residual values, but the third one only conducts the first coarse reconstruction, while the last one completes both the coarse reconstruction and all precise defect reparation. The image level classification performance are evaluated based on the accuracy on 2 types of samples, and the segmentation performance are evaluated by the two popular evaluation metrics. This image shows the reconstruction output of our proposed method. The first row shows the input image and the reconstruction output in every stage. The second row shows the ground truth and the calculated residual maps. The last row shows the ground truth and the segmentation output in every stage. And from this figure, we can find the reconstruction in the core stage can perfectly eliminate the defects and output a realistic image. Here, we can observe the missing point of this screw and the holes in the defective wood are filled in the coarse reconstruction stage by our method. But there are some small differences with the original image, and the following process optimization stages further removes this difference that appears in the non-defect region. And at the end, a perfect defect-free image will be achieved. We also compared the reconstruction output and the segmentation result with other benchmarks. From this figure, we can find our method successfully reconstructs the defect-free images. Besides, the texture and the details of the object we simulated are more realistic than other benchmarks. Moreover, the defects in our segmentation output are more accurate and distinguishable than others. This table shows the image level classification performances. It can be observed that the overall performance of our variations are better than other benchmarks. Besides, our method also decreases the rate of detection missings for defective images that are quite high in other benchmarks, especially for these four benchmarks. The segmentation performance are evaluated by these two different evaluation metrics, which are shown in these two tables. The best performance are achieved by the third variations in both tables, and the result of last variations are a little bit lower than the third one. It's probably because some parts of defects region were missed in process defect reparation. We also applied the proposed method in a real-world pharmaceutical manufacturing application. Before starting the production of an active pharmaceutical integrate, the condition of essential equipment, such as the surface of vessel, has to be inspected for avoiding coarse contamination. Here, we get a surface dataset of metal vessels. The distribution are listed here. From this table, we can find our method outperforms AE-based method with large margins in both image level classification performance and pixel level segmentation performance. And this figure also proves the concept. Comparing with other benchmarks method, the defects are perfectly repaired by our method, and our detection also depresses most of the noise that happen in other benchmarks. In conclusion, a novel multi-stage image reconstruction framework is proposed, which can reconstruct an initial defect-free image in the coarse reconstruction stage. Then, it will iteratively search and repair suspicious regions in a self-supervised manner, so that anomalies can be easily identified from the large residual map. The experimental results demonstrate that the approach achieves outstanding performance in the public dataset and the real-world pharmaceutical manufacturing dataset. Additionally, it also shows an excellent reparation capability for defective image that can be helpful for further analysis, such as operator check. That's all my presentation. Thank you for your attending.